In this section, we will cover the basics of probability. Whenever we speak about probability, we're interested in the likelihood that a certain event will occur. Whenever we discuss the ideas of probability, we do need to differentiate between two types of probability. First is the theoretical probability, and next is the empirical or experimental probability. To illustrate these two probabilities, theoretical or experimental, let's consider flipping a coin. We know from our real-life experience that if we flip a coin, we have a 50% chance of the coin landing heads up and a 50% chance of the coin landing tails up for any one flip. Now suppose we flip a coin 2 times. What is the theoretical likelihood that it will land heads up only one at a time? Think about what you would answer there. What percentage would you guess that it would land heads up one of the times? Our instinct would be to say 50%. And that would be correct because the possible outcomes is that we could have heads, 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 tails, tails, then heads, because the order matters, or tails, tails. And we see in 2 of these instances, we have heads landing up exactly 1 time. So half of the time, which is 50%. Now, it is the theoretical likelihood that 50% of the time we'll get heads up one of the 2 coin flips, but does that mean every time we flip a coin 2 times, it is guaranteed to land heads up one of those times? And the answer to this question is no, because we know we could also get heads, heads occurrence or tails, tails. So the theoretical likelihood is the likelihood that something will occur. And then if we ever wanted to see the experimental probability, we would actually run the experiment and then see what occurs. So for our class, we will have the formula that the theoretical probability can be found, and it's written the probability P of event E is equal to the number of favorable outcomes, or the number of ways our event could occur, divided by the total number of outcomes. Now, to apply this to our previous example, how many ways could we get our desired outcome? Well, our outcome was that there was heads up only one of those times, and we saw there was 2 ways that that could occur out of the total 1, 2, 3, 4 possible occurrences. So that's 2/4 or 0.5. And then remember, how do you change a decimal to a percent? If we wanted to express this as a percentage, you just move the decimal place over twice, and that's where we get our 50%. So keeping this formula in mind, let's go through some examples in probability. Using the formula above, determine that if a single coin is tossed 3 times, find the probability that it will land tails up only 1 time. So let's first classify our event. If you would, read through the sentence again and try to identify what is the event in question. So our event is that out of 3 coin flips, we have tails up only once. Let's write out our basic formula, and this is something that I would encourage you to just repeat often after you finish this lesson to help you remember. The probability that an event occurs is the number of ways that the event could occur divided by the total number of ways. So for our particular example, that would be the number of coin flip outcomes with only 1 tail after flipping a coin 3 times, out of the total number of ways we could flip a coin 3 times. In order to find either of these, the total number of ways we could get 1 tail after 3 coin flips, or the total possible of outcomes, we first want to outline in an organized fashion all possible occurrences, and that will give us our total number. And then from that list, we'll identify how many have the required criteria that there's 1 tail. Once we know that, we'll just form our fraction. So a tree diagram will be helpful here for us. To create a tree diagram, we need to think what's happening in the situation. We're tossing a coin 3 times, So I've got 3 different instances. We've got our first flip, and in the first coin toss, there's only 2 possibilities. We will either get heads or we'll get tails. One of these 2 things would occur. And the way you want to think about this tree diagram is if we assume heads occurred, then we have options for the second coin toss. So it's kind of like if heads occurred, then what could occur next in the second coin toss? And then we'll also similarly say if instead we had tails first, what would happen in the second coin toss? So we list out our second coin toss. And we know every time we toss a coin, there's only 2 possible outcomes, heads or tails. So if we had heads first, we could get heads again for the second coin toss. Or I could have had heads first, followed by tails. Or perhaps from the first coin toss, we didn't get heads at all. Instead, we got tails first. Then the second coin toss would be followed with a possibility of tails, then heads. Or instead, it could have gone tails to tails. Next, we care about the third coin toss. And again, with every coin toss, there's 2 options. We know we could get, and to help us see this, what I'm imagining now is that we got heads for the first coin toss, heads for the second. And if that occurred, we'd still have to flip the coin one more time, which would be our third coin toss. And every time you toss the coin, you could get heads or you could get tails. So there's 2 options. We could get heads, 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 or heads, heads, tails. Now this portion of the diagram was assuming that we had heads followed by heads for the first and second, and then either heads or tails for the thirds. But what if instead we had heads followed by tails? Then when we flip the coin a third time, there's 2 possible outcomes that could follow from it, either heads or tails. So we're kind of with this tree diagram showing all possibilities. Now, this entire tree depended on getting heads for the first coin toss. But we know we could have got tails for our first coin toss, in which case the second coin toss would have been either heads or tails. And then similar to the above, we would have the third coin toss of heads or tails in each of these instances. Now together, let's count how many total outcomes there are for the 3 possible coin flips. I've got our first outcome, heads, heads, heads. So that's 1. Next, we could have had heads, heads, tails. That's another possible outcome. Then heads, tails, heads. Another possible outcome. Heads, tails, tails. Another outcome. Now I'm going to repeat the colors just because I don't have more highlighters, but they're not the same. This is just to indicate. Tails, heads, heads. That's another outcome in our list. Tails, heads, tails. Tails, tails, heads. And finally, tails, tails, tails. So the total number of ways this could have occurred is 8. Now of these 8 ways, let's see which meet our criteria that we have tails up only 1 time. So we will look at each of these 8 occurrences and see who has tails up only 1 time. Heads, heads, heads has no tails. Heads, heads, tails has tails up only 1 time, so that's 1 occurrence that we wanted. Heads, tails, heads also has tails up only 1 time. Heads, tails, tails is tails up 2 times, so we don't count that. Tails, heads, heads is 1 occurrence. Tails, heads, tails is 2, so we don't count it. Tails, tails, also 2. Tails, 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 also more than 1. So of the 8 possible outcomes, only 3 met our criteria that it would land up heads up only 1 of the times. So our answer is 3/8. Using ideas similar to our last example, I'd encourage you to take a moment and pause the video so that you can determine that if a single coin is tossed 2 times, find the probability that it would be tails up at least once. pay attention to the phrasing of at least once. I would encourage you to begin by making a diagram as we did before, finding the total number of possible outcomes, and then determining from those how many of those outcomes are we interested, where tails up occurs at least one time. After you've worked on the problem, unpause to check your work. So I begin with the diagram. I know in my first coin flip I could have occurred with a heads or a tails, and then since we're tossing it 2 times, if I had gotten heads first, then the second flip could have also been heads, or it could have been tails. And if instead for my first coin flip I had had tails, that could have been followed up with a heads flip for the second, or a tails. So out of all, the total number of occurrences is 1, 2, 3, 4. Now, of these 4 occurrences, how many meet the criteria where we have tails up at least once? Well, let's translate. What does at least once mean? At least once in this circumstance, since there's 2 flips, means 1 or 2 tails, because we're okay as long as it's at least one time or more. Well, the flips that have 1 or 2 tails is here, here, and here. Only heads is excluded. So 3 of the 4 outcomes meets our criteria of at least 1 tails up. In our next example, we have that Kathy wants to have exactly 2 daughters. Assuming that a boy and girl babies are equally likely, find the probability of having exactly $2 in the following cases. She has a total of 2 children. So as before, whenever we're computing probability, it can help us to list out all the options. Now, we've done this with our diagrams, but we could also give quick variable names. Let's let having a boy be B, having a girl be G. Well, the possible outcomes is if there's 2 children, she could have a boy first, followed by another boy baby, or she could have a boy first, followed by a girl baby, or a girl first, followed by a boy baby, followed with a girl with another girl. So there's 4 possible outcomes here, so our total is 4. And then if we're looking for exactly 2 daughters, there's only 1 outcome where that occurs, so that would be 1 in 4 probability. Now, if we extend this to having 3 children, we now have more possible outcomes, so let's look at that. For the first child, it could be a boy as we had before. And once we get to 3 children, I would say the situation is such that we might be helped with the tree diagram, so let's do that. This is our first child, second, and then third, because each time that for each child, there's only 2 possible outcomes. So if you have the boy first, that could be followed with another boy or another girl. And then in the third child, that could be a boy or a girl. Similarly, if we had boy then girl, the next child could be a boy or it could be a girl. If instead of having a boy first, we had a girl first, then that follows with boy, then girl, boy, then girl, boy, then girl. And one nice thing about the tree diagram for more complicated situations compared to just listing out the options is the tree diagram helps you stay organized and make sure you're not missing any cases. So let's count the total number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible outcomes. That's the total. Now, the premise said what's the probability of exactly 2 girls? So we're looking at 2 girls, 1 boy. First option is all boys. 2 boys, 1 girl. Again, 2 boys, 1 girl. This option has 1 boy, 2 girls. This option has 1 boy, 2 girls, as does this one. So we would have 3/8 as the probability for this. Now let's look at some properties of probability. One phrase that we'll want to know is the event. So whenever we're talking about probability, an event is the set of outcomes in an experiment or in a situation that we're looking for. So if we're not doing something that seems so much of an experiment, in our last example, the event was having 2 girls out of 3 children. Now, all the possible ways that the outcome of an experiment could occur is called the sample space. And this is what we're thinking as our total. What is the total number of ways that something could occur? So if we're asked for the sample space of an event, we just need to list out all possible occurrences for that event. Now in our next example, let's consider a regular 6-sided die. And remember, a die is a cube. And on each of the 6 sides, there's a different number of dots. We've got a dot, 1 dot, 2 dots, 3 dots, 4 dots, 5, and 6 dots. So just to help us visualize this, if I rolled a dice, this would be rolling a 2. This would be rolling a 3, a 1 again, rolling a 3, and there's an option of sides with 1 through 6. Now, in any single roll, how many possible outcomes could there be if I'm rolling a die? We know that in any single roll, I could have gotten a 1, 2, 3, 4, 5, or 6. So there's 6 possible outcomes. And if we're asked what's the probability that we roll exactly a 2, there's only one way to roll a 2, so one outcome out of 6 would have us rolling a 2. If we're asked next, what is the probability of rolling another other than a 2? Well, as we just have to meet being other than a 2, that means we're okay with rolling a 1, 3, 4, 5, or 6, which is 5 outcomes out of the 6 possible outcomes. Now take a moment to consider, what is the possibility of rolling an 8 for a 6-sided die? The possibility of rolling an 8 in a 6-sided die is non-existent. In the 6-sided die, there is no side which is labeled with 8 dots, so there's 0 chances that could occur out of the 6 options, but 0 divided by any number is 0. Next, we're asked to consider what's the probability that a number less than 7 is rolled. So the only criteria we have to meet is being less than 7. So let's look at our 6 options. Is 1 less than 7? Yep. 2 is less than 7. 3 is less than 7. 4 is less than 7. 5 is less than 7. And 6 is less than 7. So all of the 6 outcomes are acceptable because they're all less than 7. So we have 6 outcomes that would be what we're looking for out of the 6 possible, but anytime you have a number divided by itself, that's just equal to 1. And in terms of probability, we have a special reasoning that goes along with if the probability is 0 or 1. If the probability is ever equal to 0 in an event, that means the event is impossible. Likewise, if we ever have a probability of 1 in an event, that means the event will certainly occur. So keep in mind, if there's a probability that's 0, it means the event is impossible. If the probability is 1, the event is certain. And then between 0 and 1 are all the various other probabilities. The lower the probability, the closer to 0, the less likely it is to occur. The closer the probability is to 1, the closer that it will occur, or the more likely it will occur. And this is what we have written here. For any event E with a sample space S, so remember, the sample space is all the possibilities, E is the event that we actually want. Then we know that the probability that E occurs must be a number between 0 and 1. And then we know the closer it is to 1, the more likely. The closer it is to 0, the less likely it will occur. If the probability is 0, that means it's impossible to occur. If the probability is 1, that means it's certain to occur. To this point in the notes, we've been dealing with theoretical probability. In a theoretical experiments, what are all the possible outcomes? How many ways could what I want to occur? And that's how we calculated the probability. Now let's turn our attention to experimental probability. And in experimental probability, We will conduct the experiment and record the results. But one thing to keep in mind is that in experiments, results do not match our theoretical expectations all of the time. There's no guarantee that the outcome of my experiment is exactly matching my theoretical expectations. Consider an example where I flip a coin 4 times. If I flipped a coin 4 times, how often would we expect to see heads, and how often would we expect to see tails? If I flipped a coin 4 times, and I was to guess about how often heads or tails would occur, since each flip has a 50% likelihood of being heads or tails, my best guess might be to think that I might have had 2 tails and 2 heads in no particular order. Now let's actually flip a coin 4 times and record the result. So let's flip the coin for the first time. Okay, we got tails. I'll record that. We'll flip the coin again. The second flip also was tails. Flip it again. Heads. And for our third flip, tails. So this was our experiment. We flipped a coin 4 times and recorded the results. And what we notice is in this experiment, I actually had tails occur 3 times. But at the outset, based on my theoretical understanding, I would, based on a probability perspective, have only expected 2 tails to occur. This is our example where in the experiments, the results do not necessarily match up with our theoretical expectations. And the reason being is even though it's less likely, in an experiment I could potentially get the scenario where I had tails, 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 or heads, 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 heads. There are more instances where I have 2 heads and 2 tails than those instances, but there's still the possibility that I could get only heads, only tails, or any mixture in between. However, one thing that we need to keep in mind is that in this particular experiment, I only did 4 coin flips, which for an experiment perspective is really not much. For instance, if I flip the coin 100 times, right now I have 3 out of 4, or 75% of the occurrences is tails. But if I flipped a coin 100 times, I would get much closer to that theoretical expectation that 50% of the coins should be tails, 50% should be heads. Even more so if I flipped the coin 1,000 times and recorded the result. If I have an experiment with more coin flips, the more coin flips that I have, the more likely that the result of my experiment will approach the theoretical expectation of 50% of heads and 50% of tails. And this is the idea of the law of large numbers. The law of large numbers tells us that as an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability of the event. So the more times I repeat the experiment, the closer the results of the experiment will match my theoretical expectations. So in closing, keep in mind our formula for probability is the probability that an event occurs is the total number of ways the event I'm looking for can occur divided by the total number of possible outcomes.